Hello everyone, this is Professor Roman. Let's continue the group theory lectures. We have been talking about the symmetric groups, and I now want to talk about something that is not generally covered in undergraduate group theory courses, at least not to my knowledge, but is a wonderful example of mathematical discovery. This is conjugation in the alternating group. And to start, I think it would be a good idea just to speak in general terms to give you an idea of the issue involved, really. So, suppose G is a group, H is a subgroup of G, and we have two elements A and B in H. If I said to you that A and B are conjugate, you might reply, conjugate where? Conjugate in G or conjugate in H? And these are in fact different things. To say that A and B are conjugate in G would mean to say there's an element little g in capital G for which B equals the conjugate of A by G. And I'm just going to say this as A to the G to cut down on some of the wind. But to say that A and B are conjugate in H is to say there's an element little h in H for which B equals A to the H. These are different conjugacy relations. So to avoid some obvious confusion, I will use the terms G conjugate and H conjugate. Now it's clear that H conjugacy implies G conjugacy, but the converse is not true, and we'll see that in a moment. So the issue in general terms is we may know how to tell whether two elements in G are conjugate, but if the elements happen to lie in H, we may not know how to tell whether they are H conjugate. And that may require further investigation. And that's exactly the situation we're addressing now. We've seen that two permutations in Sn are Sn conjugate if and only if they have the same cycle structure. And nothing could be simpler than that. But oftentimes, we will need to know when two even permutations are An conjugate. There are Sn conjugate even permutations that are not An conjugate, so the issue is a little more complex here. So the question of An conjugacy is not just a simple matter of looking at cycle structures. Well, it involves cycle structures, but it's a little more work. Just as an example, the even permutations 1, 2, 3 and 1, 3, 2, these three cycles, they're S3 conjugate because they have the same cycle structure, but they're not A3 conjugate because there's no even permutation lambda that satisfies this equation. And you can check that because A3 is a very small group. To understand the nature of An conjugacy, I'm going to define two binary relations on Sn. And I don't know whether you'd see these anywhere else. They're obvious binary relations, but I don't know if you'll see them elsewhere or not. Two permutations, alpha and beta, in Sn are evenly conjugate if there's an even permutation lambda for which beta equals alpha to the lambda. And they're oddly conjugate if there's an odd permutation lambda for which beta equals alpha to the lambda. And again, these terms are not standard, so but they will be very convenient in our discussion. And I hope they're pretty intuitive definitions. And I'll use this notation. I'll put a subscript E underneath the conjugate symbol for evenly conjugate, and similarly for oddly conjugate, we'll use a subscript O. This terminology is well-founded because even conjugacy and odd conjugacy are symmetric relations. So I can simply say alpha and beta are evenly conjugate, and I don't have to say alpha is evenly conjugate to beta if I don't want to. Okay. Now, in fact, since AN, the alternating group, is a group, even conjugacy is an equivalence relation. It is reflexive, it is symmetric, and it is transitive. Odd conjugacy, however, is not an equivalence relation. It fails to be either reflexive or transitive. It's symmetric, that's it. But we do have the following rules. They're transitivity-like rules involving odd conjugacy, and they follow the same parity rules as ordinary addition of integers. Odd plus odd is even, odd plus even is odd. So here we have odd, odd, even, and here we have a mix, one of each, even odd or odd even. Both cases the result is odd conjugacy. Okay, so now let's take a look at conjugacy classes, which is what we're really interested in. If an SN conjugacy class, and I'll call it K, contains an even permutation, then all permutations in K are even because they have the same cycle structure. So K is completely contained in AN. And I'm going to refer to such SN conjugacy classes as even SN conjugacy classes. All other SN conjugacy classes contain only odd permutations. So they would be called odd SN conjugacy classes, but they're not going to be relevant to our discussion, so we don't need to worry about that. So there are two types of SN conjugacy classes, consisting of all even permutations, which we'll call an even conjugacy class, and all odd permutations. And we don't have any use for the odd conjugacy classes. So we'll focus on the even ones, because they belong to SN, as subsets of SN. As to the AN conjugacy classes, of course, they all lie in AN. They consist only of even permutations. Also, each AN conjugacy class is contained in a unique, even, necessarily even, SN conjugacy class, because AN conjugacy is SN conjugacy. So if two elements, two permutations are AN conjugate, they're also SN conjugate, and so they belong to the same SN conjugacy class. This means that also the AN conjugacy classes that are contained in K partition K. Pairwise disjoint union is all of K. So there are potentially two types of even SN conjugacy classes. There are the ones that are actually AN conjugacy classes themselves. So the partition is just one block, and there are SN conjugacy classes, even SN conjugacy classes, that are partitioned into more than one AN conjugacy class. So here in this picture, here is SN. Half of it here on the left is AN. And this is an even, the shaded portion, an even SN conjugacy class. Everything in here is an even permutation. Every two elements here are conjugate under SN. Okay. Suppose that the AN conjugacy classes which partition K, suppose there are 3 of them or more. So I've drawn this here with exactly 3 AN conjugacy classes, but there could be more. The point is, we can now take 3 elements, 3 elements from different AN conjugacy classes, alpha, beta, gamma. And we have a problem because alpha is oddly conjugate because no pair of these 3 elements can be evenly conjugate. Alpha and beta cannot be evenly conjugate, or they'd be in the same AN conjugacy class. Similarly for the other pairs. So alpha and beta must be oddly conjugate. They're conjugate because they belong to an SN conjugacy class, K. So alpha and beta are oddly conjugate, beta and gamma are oddly conjugate. But then alpha and gamma are evenly conjugate, and that's a contradiction. The only way out? No even SN conjugacy class can be partitioned into more than 2 AN conjugacy classes. So there are 2 types of SN conjugacy classes. There are the ones that are also AN conjugacy classes, and I'm going to call those type 1 for want of a better term. The 1 refers to one AN conjugacy class. And then there are those SN conjugacy classes, the even ones, that are partitioned into exactly 2 AN conjugacy classes. And I'll call those type 2. So I could have drawn another picture here, which I will try to do. This is AN here. It is partitioned into conjugacy classes, SN conjugacy classes. Okay. These are the even SN conjugacy classes. Some of these may be type 1, in which case they're also AN conjugacy classes. Others may be type 2, in which case they are made up of the union of 2 AN conjugacy classes. So maybe this one's type 1 and this one's type 2. So the AN conjugacy classes, looking at it from that point of view, some of them are also SN conjugacy classes. Others are a portion of an SN conjugacy class, and they're paired off with another AN conjugacy class whose union is the SN conjugacy class. This may seem a bit abstract, so that's okay. It may take you may have to listen to this lecture more than once to really get a feel for what's going on, because we're not done yet. Here's another picture. SN our even SN conjugacy class. This has type 1. It is also an AN conjugacy class. This one is type 2. It is split into 2 AN conjugacy classes. Now we would like to find a way to distinguish if given an even SN conjugacy class, can we tell which one it is type 1 or type 2? And the answer is actually going to be quite nice when we get to it. Since a type 1 SN conjugacy class, K, is also an AN conjugacy class, it means that every pair of elements in K is evenly conjugate. But if we take a permutation in K, and if we take an odd permutation, any odd permutation, tau, could be a transposition, for example, then alpha and its conjugate by tau, they are evenly conjugate, from what we just said, but they're also oddly self-conjugate because tau is odd. So this is what it looks like in symbols. But even conjugacy is symmetric, so we could interchange these two and then apply these transitivity-like rules. Alpha oddly conjugate to alpha tau, which is then evenly conjugate to alpha. So alpha must be oddly conjugate to itself. And so we'll say that alpha is oddly self-conjugate. So every element of a type 1 SN conjugacy class, K, is oddly self-conjugate. That seems like a strange property, but another way to say it is that a permutation is oddly self-conjugate if and only if it commutes with some odd permutation. So that's not, maybe that's a little more reasonable point of view. Conversely, suppose that K is an even SN conjugacy class in which every element is oddly self-conjugate. Well, every pair of elements, alpha and beta and K, is either evenly conjugate or oddly conjugate. If the two are oddly conjugate, then we can write alpha oddly conjugate to itself. We've assumed that for all permutations in K. Alpha oddly conjugate to beta, therefore alpha evenly conjugate to beta. So there's no escaping it. Any two elements, alpha, beta, and K, are either evenly conjugate or oddly conjugate and therefore evenly conjugate. So every two elements in K are evenly conjugate. Therefore, K is also an AN conjugacy class. It's an SN conjugacy class in which every two elements are evenly conjugate, so it cannot split into two AN conjugacy classes, because then it wouldn't be true that every pair of elements was conjugate. So it is a type 1 SN conjugacy class. It is also an AN conjugacy class. So K then, our even SN conjugacy class, is type 1 if and only if every member of K is oddly self-conjugate. Or, in other words, every member of K commutes with some odd permutation. Now, if a single member, alpha in K, is oddly self-conjugate, then every element of K is oddly self-conjugate. Call an arbitrary element beta. We have alpha oddly self-conjugate and beta another element of the conjugacy class. Well, again, alpha and beta are either evenly or oddly conjugate. If they're oddly conjugate, we can write this string, which shows that beta is oddly self-conjugate. If alpha and beta are evenly conjugate, we have this string, and so again, beta is oddly self-conjugate. So if a single member of K is oddly self-conjugate, they're all members are oddly self-conjugate, and we know then we have a type 1 conjugacy class. So here it is in summary. Let K be an even SN conjugacy class. So all that means is that it's an SN conjugacy class that is contained in AN. Then K is also an AN conjugacy class, in other words, it has type 1, if and only if at least one, and therefore all members of K, are oddly self-conjugate, or commute with an odd permutation. If K is not an AN conjugacy class, then K is the disjoint union of exactly two AN conjugacy classes. So we've made a lot of progress here in understanding the nature of AN conjugacy classes. They're either the same as SN conjugacy classes, or they have a partner, another AN conjugacy class whose union is an SN conjugacy class. But we can still do better. I mean, after all, we should be a little worried because checking for odd self-conjugacy might not be easy. For SN conjugacy, we check cycle structure. That's easy. So let's keep digging. We need to take a closer look at odd self-conjugacy. What does it mean to say that a permutation is oddly conjugate to itself? There are, in fact, a lot of oddly self-conjugate permutations. For example, any odd permutation, alpha, is oddly self-conjugate because if we conjugate alpha by itself, which is an odd conjugate, we get alpha. So this applies in particular to any even length cycle. Remember, even length cycles are odd permutations. In addition to that, if we have an odd permutation alpha and any other permutation beta that's disjoint from alpha, then when we conjugate the product alpha beta by alpha, it does nothing to beta, so we get alpha to the alpha beta, which is alpha beta, so the product is also oddly self-conjugate. Therefore, any permutation whose cycle decomposition contains an even length cycle will be oddly self-conjugate. that covers quite a lot of ground. You just form the cycle, decomposition. If there's an even length cycle in there, your permutation is oddly self-conjugate. Also, the product of two disjoint cycles of the same length, odd length, will be oddly self-conjugate. Because if alpha looks like this is a product of two cycles of odd length, same odd length, 2k plus 1. We could define a permutation as a product of transpositions. I want to swap A1 and B1. I want to swap A2 and B2 all the way down the line. So that's what this does. So when we conjugate alpha by lambda, all we're going to do, remember that just amounts to applying lambda to all the A's and all the B's, it's just going to reverse the order of these two cycles. And we're going to have the B cycle preceding the A cycle. Well, if the cycles are disjoint, they commute, so that's also equal to alpha. So alpha is oddly self-conjugate. So if the cycle decomposition of alpha has an even permutation or contains an even permutation, and if the cycle structure has two disjoint cycles of the same odd length, in either of those cases, this similar argument applies here as we did here for this portion. Then the permutation is oddly self-conjugate. What does that leave? Does it leave anything for even self-conjugacy? What's the negation of these two conditions? Either cycle decomposition either contains an even cycle or two disjoint. They're always going to be disjoint in the cycle structure. So two cycles of the same odd length. The only thing left is that the cycle decomposition contains only odd cycles, all of which have different lengths. You know, 1 cycle, a 3 cycle, a 5 cycle, a 13 cycle, a 43 cycle, all odd, all different lengths. Could such a permutation be oddly self-conjugate? Well, that's a question we need to answer. So let's suppose alpha is this is the cycle decomposition. It's a product gamma 1 through gamma m. These are all, m is odd. Okay. I'm sorry. The lengths of the cycles are odd, and they're all different. Can such a permutation be oddly self-conjugate or not? It's the only case we're missing. Well, we had a theorem in chapter 8, 8.43, that said that the only permutations that commute with alpha, in other words, the centralizer of alpha, looks like this. The permutations, you take these cycles and you can raise them to any power you want, and then take the product here. All of these commute with alpha, and that these are the only permutations that commute with alpha. That may have seemed like a strange thing to do in chapter 8, but now you see why I included it in chapter 8, so that I could use it here. But each of these cycles, the gamma i's have odd length, so they're even permutations, and therefore so are these permutations even. product of even permutations is even. Therefore, alpha does not commute with any odd permutations, only these permutations, and they're even. So alpha is not oddly self-conjugate. Now we have a really good description of the two types of AN conjugacy classes. K is an even SN conjugacy class. It's one of two types. Type 1, K is also an AN conjugacy class. And this is the condition we saw earlier that might or might not be easy to check. These are precisely the conjugacy classes in which one and therefore all members of K commute with an odd permutation, an oddly self-conjugate. Type 2, K consists of exactly two AN conjugacy classes. These are precisely the conjugacy classes whose cycle structure consists of odd-length cycles of distinct lengths. So we have come a long way in this journey here, but we came to a very satisfactory conclusion. We have a nice characterization. We know there are two types of even SN conjugacy classes. We know what they look like. We know how to tell which type a given conjugacy class is. Example, the even S3 conjugacy class that contains the 3 cycles is just this little guy here. There are only 2 3 cycles in S3. Cycle structure, 1 cycle of length 3. So that consists of only odd cycles of different lengths. Okay. So this is a type 2 conjugacy class. Type 2 class, therefore it splits into 2 AN conjugacy classes. Well, I guess we know what that has to be. Each of these is an AN conjugacy class. Okay, so for example, the only permutation in S3 that is evenly conjugate to this cycle is the cycle itself. The even S4 conjugacy class that contains the 3 cycles looks like this. These are all the possible 3 cycles in S4. Now the cycle structure is a cycle of length 3 and a cycle of length 1. Okay, so for example, the full cycle decomposition here would be 1, 2, 3, and then 4 by itself, right? So the cycle structure, remember me saying a long time ago when we talked about cycle structure, you have to include the 1 cycles. That's critical. So these aren't the cycle structures, these are just the cycles, the 3 cycles. The cycle structure is 1 cycle of length 3, 1 cycle of length 1. So these are odd length and they're distinct lengths. So again, we have a type 2 SN conjugacy class. And so it splits into 2 A4 conjugacy classes. And I'll let you figure out what the split is. Okay. when n is bigger than or equal to 5, the 3 cycles in Sn have this cycle structure. 1 cycle of length 3 and n minus 3 cycles of length 1. So if n is bigger than or equal to 5, there's at least 2 cycles of length 1. So even though all the cycle lengths are odd, they're not all distinct. So this is an Sn conjugacy class of type 1. In other words, it's an An conjugacy class. Or put another way, when n is bigger than or equal to 5, all 3 cycles in are conjugate in An as well as Sn. And we can squeeze out some more from the theorem. The possible cycle structures in S5 look like this. And the cycle structures that correspond to the even conjugacy classes are these. Remember, an Sn conjugacy class is essentially characterized by the cycle structure of any one of the permutations in that conjugacy class. So if I give you the cycle structure, I've told you which conjugacy class I'm discussing. Now, only one of these cycle structures satisfies the condition to be a type 2 conjugacy class. Okay? And that's this first one. Odd cycle length, all cycle lengths are different. This consists of odd cycles of different lengths. Only one cycle, length 5. Here we have 2 cycles of length 1, even though both odd. Here we have some even cycles, and here we have a bunch of cycles of length 1. So only one of these is a type 2 conjugacy class, splits into 2 An conjugacy classes. These are An conjugacy classes. They're type 1. So we know there are exactly 5 An conjugacy classes. 2 from here, 3, 4, 5. That's pretty powerful. Okay. So this theorem that we have discovered can be quite powerful. The statement concerning the 3 cycles, the An conjugacy of 3 cycles is very important. Well, we just covered a minute ago, so we're going to use it later, so I'll make it into a theorem. If n is bigger than or equal to 5, then all 3 cycles are An conjugate. We've known for a long time they're Sn conjugate because they're the same conjugacy, the same cycle structure. But now we know they're An conjugate. So in particular, if n is a non-trivial normal subgroup of An, and if it contains a 3 cycle, then it's all of An, because it's closed under conjugacy, being normal, and so it contains all the 3 cycles, which we have seen generate An. So again, if we have a non-trivial normal subgroup of An that contains a single 3 cycle, it's all of An. This is going to be very important when we discuss the simplicity of An.